Sorry, everyone. I've been talking to myself for the last 2 minutes. I apologize. I thought I was live. I just was broadcasting to YouTube, not actually live. Um, Hi. So, hi. My name is Zach. I'm an open source software developer who's trying to get serious about his hardware. And so, in that effect, I'm trying to really learn Verilog in depth and proper enough depth that I can use it commercially and with enough confidence. Yeah. So that's me. What are we going to do today? We are going to do the assignment of week two, the challenge of week two, which is create a design that combines what we learned through the kind of lecture we went through yesterday. But basically the thing we need to do is make an adder module and have the adder module operate on two unsigned numbers. And then we need to go through the rest of the discussion and stuff. I think what would be very interesting isn't the adder module. The adder module could be done in 4 or 5 lines. In fact, it could be done in 4 or 5 lines. In fact, I'll do it very quickly at the beginning of the thing, and then we could go forward with that. I think what would be very interesting is understanding what the module is, understanding how the module works, and adding a test bench to our module. Why? Because building so there is this book here. So number one, I think there's a simulation here. So hardware is very hard to debug, and simulation when you're making hardware is vital. A successful complex project will always require simulation. So let's try and learn how to do things the easy way, which means just be good at simulating stuff. Because once we're good at simulating stuff, we can basically do some sort of test-driven development of our hardware. And if we can do some sort of test-driven development of our hardware, then life becomes quite easy. Because then you don't have to go jumping through LEDs, debugging LEDs and things of the sort, or looking at debuggers at every point. You can actually write a test bench that exercises your code or your design under given situations, and it can tell you what the design is doing, and you can kind of very confidently be aware of what your design is doing. So I think a very interesting part of today's thing would be to actually start very early on in this advent of FPGA thing that I'm trying to do, is to get really insanely comfortable doing simulation and test benches. Once we're getting really comfortable, there's actually a specialist role that is called verification engineers. Verification engineering. Well, engineers. Yes, I am not a robot. This is me on my computer. I beg, I am not a robot. So there's a complete entire field of engineering that is based on people who can. What is a verification engineer? The verification engineer operates before the FPGA, ASIC, or SoC production phase. He works with the design team, FPGA engineers and microelectric engineers, in order to verify their designs. The verification can be realized at different abstraction levels. And so, basically what I'm saying is this is a field in itself, and getting good at simulating, getting good at testing your designs is in itself is a job. So the moment you can understand things like this and get to a place where you can apply them, it becomes really easy. So what are we going to do today? We're going to implement an adder module. We're going to implement a test bench for this adder module, and then we're going to discuss how to do this and all of the things that come up together with this. So let's sort of get started. I'm going to clean up everything, and I'm going to leave this, and I'm gonna go out of this, and then let's make a directory, make dir adder. Let's call it the adder, RTL adder. Yeah, RTL adder. let's call it that. I'll commit this at some point and I'll put it up. If I think so, it should work. It should work. So we have that, and then let's go into RTL adder, and then in here let's initiate a new project called using Appio. Can I do a Control R? Appio create. Yeah, and then let's make the top module adder. Okay, so let's do that, and then ls, we should have that in here. The next, and the cut appio.ini. If we look at the appio.ini, it's initialized for the Arduino 3 board, which is this one, and the top module is going to be adder. So cool. So let's actually keep going. So let's open our editor and start adding files to this. The first thing I'm going to add is an adder.v, which is an adder.verilog. And then in here, the first thing I'm going to do in this module is I'm going to set a default net type to none. Okay, I'm going to do that. I'm going to set a default net type to none, and I want to do that so that actually this is going to help our, how do we call this? How would I label it? This is going to cause that any undefined symbols, we'll see it just now. Basically, this directive will cause that any undefined symbols just get flagged and they don't get run. And we can actually go look at how a module is defined in here. Let's actually think about a very simple module. So this is the way. So this is how our module is going to be defined, and our module is going to have two outputs, two inputs and one output. So let's look at it here. So inputs, two 8-bit unsigned numbers to be added, output the sum of the two numbers. So perhaps let's start out by creating a module that has two 8-bit inputs and maybe one 8-bit output, a 9-bit output. Why do I say a 9-bit output? What is the max number that we can represent with 8-bit, an 8-bit value? It's going to be 255. The reason it's going to be 255, it's going to be 2 power 8 minus 1. 2 power 8 is 256 minus 1. I can do this here. 2 power 8. We did this yesterday actually. 2 power 8. So 2 power 8 is 256. And then if we do minus 1, that is the max number is going to be 255. And then let's say 255 plus 255 is equal to 510. So the thing here that we need to ensure is that we can represent the number 510. And in order for us to do that, we need to do 2 power 9. And 2 power 9 can represent, what can 2 power 9 represent? 2 power 9 is 512. So let's do a module with three values, 2 inputs and an output. And I think we can look at bus signals to tell us about this. Let's put it this way. So let's go in here, and then we can do module adder, and this module can take in, I would say, let's think about it. So I'm doing this from scratch. Module adder can take in I1 and I1, which is input 1. Let's actually be specific. Input 1, input 2, and output. So this is what our module can take. And good. And then I'm going to do another thing here, and I'm going to do an AND module. I don't think AND module gets a thing to be like that. So let's look at it. AND module, it doesn't get a thing. So that's fine. That's fine. And then let's look at how, so as we define them. So what are bus signals? So initially you can define a signal so it's just a unit of one, or just one. Okay, by default it is one, it is a bit. But whenever you're working with whenever you want to work with where are bar signals, please show me the bar signals. Yeah, so whenever you're working with a group of inputs or outputs, you can group them into something called a wire. You can make wires to have more than one bit and stuff. So let's make sure. So let's make 3 wires, and one wire is going to be a 9 bit, and then there's going to be 2 inputs of 8 bits. So let's do that. Let's do that in here. Let's do that in here. Unfortunately, I don't know why my syntax highlighter is going, but we'll just check it out just now. It's gonna come back. I'm going to say output input 1 input wire input wire. You actually want to do this input wire, and then in here we're going to say 70, and then in here we're going to label it as input 1, and then let's do another input there, and then we're going to label this a wire, and then we're going to say this is a 7 and a 0, and then we're going to label this input 2, and then we're going to say we're going to label a third one output, and then we're going to say this is a wire, and then we're going to label this, we're going to say its capacity is 9, or wait, actually let's say 8. Its capacity is 0 to 8, which becomes 9 bits, and then we're going to label this output. And in essence, output input num. I won the input number, so the unsigned bit numbers. Num1. Let's call them by better names. Num2, and then let's call this sum. Let's call this sum. Okay, and then here we can come and label them as num1, and label this one as num2, and label that one as sum. I don't know why sometimes my editor will do this thing where it doesn't want to realize that actually this is highlightable code. There you go. Now it knows. Now it suddenly knows. So what is happening here? We have three variables that we can use. We have 2 inputs, 8 bits. We've suddenly satisfied this. An other module that has inputs, 2 8-bit unsigned numbers to be added, and then output the sum of the two numbers. Okay, so we have this already, and I think we can almost already do this, because if we go to the Verilog quick reference, let's go find the quick reference, and let's go find the operators. This is insanely zoomed out, so let me just make it like that so that people can see, and maybe a little bit less so that it's all visible. That's much better. Operators, expressions and operators. So let's look at that. Expressions. Oh my word. Where are you? Anyways, go down. Expressions and operators. Yeah. So which expression and operator do we want? A sum. There you go. Operator plus gives us a sum. We're already at a point where we can get this. But so how do we do a finalization? We assign a sum to some expression. What is an assign? Can we look at an assign? What does the assign keyword do? Assign keyword. So let's look at assign keyword. Yeah, keyword, assign keyword. There it is, assign, but is there something that tells us what this does? Yeah, C, assign B to C, assign B to C, but what does, I want to know what the other, yeah, so here, no, let's look at it, assign B to C. So assign means assign B to C, or rather assign, let's SW switch C. Okay, cool. So let's do here. Let's make an assign sum is equal num1 plus num2. So a little disappointingly, I think we have an other module, and it should build. Let's see, up here build. No constraints file, main.pcf. So we don't really need a PCF. We don't really need pins, but we do need a constraints file. So we don't really need pins. So let's just do main.pcf, and we can leave it blank. I apologize for disappearing like that. I had to deal with something at the door. Let's make a main.pcf pin constraints file. We'll get to this file later, and let's save it, and then let's go there, and then let's see if we can actually build our design. In sum 8 is unconstrained in PCF file. PCF allow unsum constraint. Let's think about this. So PCF file. But I do not need module with input. Do I need to label it an input really? Let's see. Verilog module with inputs not from pins. And do I just need to use registers? What if I just use registers instead of input and outputs? But then I need to know, yeah, I just need to, I don't need to use it outside of this, but no. Set IO PCF. Okay, let's look at this. Set IO PCF. This file, the PCF file in which user should craft the to assign IO of their things. Assign a net defined as an input or output in a net pin. Do I need to set the pin? So, which means if I go and I say can I do, yeah, can we try with PCF, PCF, allow and constraint. Can I do that? Okay, so let's think about this. I want to know what the input keyword means. So this is, you see, this is exactly why we do this. Input. The input keyword. Input signals, but I don't want to use, I just want to make a module input, not pins that are modules, not pins that are input. In Verilog input not from PCF. Okay, set IO. Can I just use the normal one? So this is B0, B1, C1. What does that do? Net. What is a net? What is a net? What is a net? What is a net? Okay, and can I just use, can I use wires, just wires that are not inputs or outputs? Can I just use wires that are not inputs or outputs? But these are outputs. So what happens there? I just use registers, I just use wires, I just leave them as wires, and I just leave them as that, and I don't have to do something. So let's look at it. What happens if I do that? Let's not label them inputs or outputs for now, just wires of certain sizes. And then let's go and do an up your linked. And I don't have to take any inputs or outputs here, so because I don't want to do anything there. But then this is going to be a problem later, because I'm going to need to actually 0 equals 0 equals 0 equals 0 equals 0. Okay, so the equals 0 equals 0 equals 0. So I can just set them initially to tab equals 0 equals 0 equals 0. Okay, cool. So what's happening here? What is happening here? Can I link it? Okay, linked. What happens? Okay, so cool. So this gives us this becomes our first thing. If we use input and output keyword, the module can have inputs and outputs, but if we end up using inputs and outputs keywords, we are going to have to deal with inputs and outputs on the board or on the FPGA itself. But it seems like we can actually have a module that has a module that presents what do we call it? A module that has inputs and outputs, or rather it has a place where it puts a couple of inputs and it has a place where it puts a couple of outputs, and using those spaces we can just operate on them rather than actually defining actual inputs and outputs, because we don't necessarily want inputs and outputs at the moment. This module lives somewhere. This module is going to be under some numerous number of modules inside the code. So it's not going to be something that's exposed to the world really. It's just going to be something that we use from somewhere. So even if it just has memory and it can just operate on that memory, and we can somehow share this memory, port it out. So Verilog modules have this thing called ports. Verilog modules have this thing called ports. A Verilog port. A Verilog module only optionally needs to have a list of a Verilog port. A port list, for example, a top level test bench may not have any Verilog ports at all. Verilog ports allow different modules of a design to communicate with each other. There are more backdoor ways that modules can communicate, but for a design that intends to be synthesized, Verilog ports is the standard name method. Okay, so the thing I'm saying here is this module can exist inside our design, but it might not even have inputs or outputs, and I think that is what is meant by internal wires here. I wonder, internal signals. So I just found it by mistake. Yeah, so it turns out there is a name for what I'm looking for. It's internal signals. So this internal wires are neither input nor output. These wires can now be used as logic, as you see. They can be assigned and then they can be used as logic, basically. But how do we tell? How do we tell? So let's look here. This, and then if I look at my test bench, how was I assigning them? This is the initial, all of this stuff. At what point do I assign, say, I do not assign the clock. And I do not assign the clock cycles. And I do not assign. Let's start with the 1-bit number. Because we kind of need this input and output. Maybe not. Verilog using internal wires in a test bench. Yeah, but that's ports. That is just a port. I want to know how an internal wire works. So we can monitor them, but we cannot. We cannot actually. Hey Tilak, how are you? Tilak is like, soon I'll be famous. Um, it's very kind words, man. That's very kind words. Thank you so much. ATB. What does ATB mean? Hi Tilak. What does ATB mean? Uh, what does ATB mean? Uh, so let's find out. Let's find out. Let's find out how. ATB. All the best. Oh wow! Thank you so much. That's amazing. Thank you, Tilak. Tilak says, "Soon I'll be famous." All the best. Thank you so much. As long as I'm helpful, if you're learning something, I'm really happy about that. I don't know about being famous. It's whatever, but as long as I'm learning and you're learning and we're both learning together, it's going to be amazing. So, setting internal wires in Verilog. So this wire exists quite inside the module. Yeah, see inner module. So let's look at this inner module. Include inner module.v. Okay, cool. So inner module has an input and an output. Yeah, that's fine. But if I do this, then I have to deal with pin constraints. If I do this, then I have to deal with pin constraints. Using input and output without pin constraints. This is how you know yeah, but then I can do input and output, which is exactly what we need. Oh my word. I'm gonna find a way. Okay, so cool. So let's actually go and build again. Up your mint. Up your build. How do I pass in? So how do I find out how to do that? Up here, PCF allow unconstrained. So I'm trying to find out this, yeah. inputs and outputs for ports. I'm trying to find out, I am really trying to find out how to deal with this input, because my inputs and outputs are only going to be for ports. They're not going to be for top module stuff. So maybe what if I do like module adder, but I go like, yeah, let's go like module my adder, and then I'm going to say let's say module adder, and then we go that, and then we go like end module. What happens here is that we're going to have two modules, and then we're going to see end module expecting that. Okay, how to detect top module, specify that, that's fine. It's fine. It's you. Let's remove that. It's you. I have an idea. So okay, so let's save that, and then let's pv, let's go in here, let's change our top module to main. That way main, and then once you go here and make a main, we want to delete that, yes, delete that, yes, and then I want to make a main.v, and then I want to go like module main doesn't take anything, and then there's that, and then I'm going to do end module, and then there's that. I don't think end module needs anything. If I'm not wrong, first design end module does not need anything. That's fine. So, but the first one does need something, so that's cool. What? Yeah, that is okay. That there's a main module here, and then there's not a main module. So let's see what happens here. I don't understand. Oh, okay, cool. I think I understand. Module main. I don't understand. Module main, yeah, module main, that's it. Module main, and then we'll go like, let's go in here. So like, let's make a 3-bit register in here. Reg. Let's do a 3.0, and then let's do that, and then say sum reg, so that this becomes an actual module. Yeah, it links fine. Up your build maybe. Yes, we fixed it. So it turns out, and we're gonna ignore main exists. It turns out that if you have a top module, and the top module has an input or an output, this module needs to end up being. This module needs to end up being. How do I say this? It needs to end up, the inputs and the outputs always need to end up in the pin constraints file. It turns out, if it's your top module. If it's not your top module, then you don't have to have it. So now we actually go into the meat of the session. What we want to do here is we want to build a test bench, because this actually does do what we want it to do. It takes in an input, it takes in two 8-bit inputs, it sums them, and it sets them to some sum, and then we can observe that sum. So what we actually want to do is we want to design a test bench so that we can actually end up exercising this this test bench, this module itself. So what I want to do is I want to do like other tb.v, and then I want to do that, and then I want to now start thinking about, I should have some samples here. I should have Verilog module and module generation. I wanted to look at a test bench itself. Let's actually look at my test bench that I use for my CPU. So let's start with that. Let's set a time scale. I don't remember why I set this, but time scale is 1ns. Time scale is going to be 1ns over 1ps. Yes, yeah. You know what? Since we're here, let's find out. Yeah. What's the use of doing it if we're not finding out? Time scale setting. Very low. Very low time scale. A Verilog simulation depends on how time is defined, because the simulator needs to know what number 1 is. So this is a delay. So this is some sort of delay, means in terms of time. The timescale compiler directive specifies the time unit and precision for the time modules that follow it. So timescale, time unit, timescale 1ns, 1ps. So it's 1ns. The unit is nanoseconds, and the time precision is picoseconds, I think, if I'm right. PS, picoseconds, yeah. And the unit is nanoseconds, which is nanoseconds. There you go. There you go. We know that. So this defines and I'm going to exit, because I know if I wanted to start doing I would like it to start recognizing my syntax, but it's not doing that for now. I'll update. The thing is, I updated from my previous computer, which was had an older version of NVIM, and now I'm on NVIM something like 0.11, and 0.11 the language processing server, the LSP language server processor is changed, so I haven't hooked it up to work very well right now. I'm sorry about that. So that's why I have to do this like weird things of like quitting and getting back, quitting and getting back, quitting and getting back. Okay, so cool. So now what we want to do is module other tb. I think that is other tb, and this is the module that we want to define. And in here, what we want to define is what we want to instantiate the. So here we go. This now becomes the meat of the thing. So what we want to do is instantiating. A Verilog module can instantiate other Verilog modules by creating a hierarchy of modules to form the full design and test bench. To form the full design and test bench. So think about it. If we learn how to write this test bench properly, we will learn how to write the actual designs themselves properly. So whenever your design goes to a point that it has more than one module, and other modules can instantiate that, it's almost like you're picking a library and you're using that library. So right now what we are learning is how to use some other module. Let's say in our case here, at some point we will want to do from the main to be able to use the other module. And to be able to use the other module from the main, we will need to instantiate the other module from the main. And this is the thing that this document is showing us, how to instantiate the module from the other one module from the other one. if that makes any sense. Shall I pose for questions? Is there any questions? Do you have any questions before I keep going? It's been 45 minutes. Do you have any questions? If Tilak is still around, do you have any questions or comments? No questions? No comments? Oh yeah, I was made aware that whenever I ask for questions like this, it takes like 30 seconds. So whenever you have a question, just raise it and I will go on. So the next thing we need to do is we need to instantiate our module under test. So our module under test. So or rather our design under test, okay? So we're gonna go into here and I'm going to do something like other, well, first of all, let's actually declare some inputs and outputs, yeah? So let's declare some inputs and outputs, I think so. Let's declare some inputs and outputs. So some wires in here. I think we're gonna do wire num1, wire 07, so first of all 07 num1, and we'll connect this just now wire another 8-bit wire 07 num2. I don't know if the names need to be the same. I think they, let's go with test num1, test num2, and then wire, and then another wire. I think I'll go with something like 08, and then I'm going to say test. So we now these are like variables that exist in our test module. Let's now instantiate our actual little module, our module under test. Other device under test. That's just some convention, device under test. And in here now we're going to actually use something called ports. This is something that has actually plagued me for quite a while. Ports. Whenever you do video software, there's things called pipelines, there's things called ports, and these are things that sort of appear from nowhere. They sort of end up connecting lower levels of hardware. Like you'll have an interface, you'll have like an I2C interface, and it will have a port in, and that port in will be fed from something like DCMI. And now I'm only realizing that this is how it works, because now there's what is happening here is that there's actually at the IP level, at the hardware level, there's something called ports, and these ports connect between modules. So now this is what we're doing here. We're connecting between modules. It's very difficult to understand them in software because they just sort of appear, you know, they just sort of appear, and then you know, you just use them, and because you're writing software, you just use them and you're done. But really, this gives us a way to understand what is happening there. There's some saying by someone famous about something like, if you're serious about your software, you should make your own hardware. And I think that's actually quite wait. So which one is which? Verilog ports. Verilog module ports. So which one is which? I want to know which one is on this module and which one is on the other module. So inputs, outputs. So module ABC and then output ABC. So test module ABC, module test ABC. Yeah, but no, I wanna know. Do we have to name them the same? It seems like everyone is naming them the same, and if we name them the same, then for now we don't even really need to know. I'm not gonna be clever. I'm not gonna try and be clever. So I'm just going to name them the same. It would have been very awesome to be able to name them whatever we wanted, but we'll find out. We will find out. And then once we find out, we'll be able to, we'll be able to, num1, we'll be able to see where to go with that, yeah, isn't it? No, this is now in here, num2, and num2, please connect it to the right place, and then there's going to be a dot sum. So someone who knows Verilog, please let me know which one is the one I just declared and which one is the one that is coming from another module. Please let me know. Someone who knows Verilog very well, please do let me know. So, and then we're gonna have this, and we're gonna close that, and we're gonna say that, and then suddenly what we have here is we have a test module, which I think needs an end module at the bottom. We have a test module here, which needs an end module, and this test module has access to the other module, the module that came before it. So it has, this test module happens to be able to, it can access the inputs and the outputs from the module that we have declared ourselves. So now what we can do is we can write some test code that actually exercises this, our module. We can write some test code that actually exercises our module and see if our module actually does the thing that it's supposed to do correctly. At which point that enables us to, you can imagine if the way this goes, we start applying and expanding this, and at some point we're testing the whole CPU or the whole data path or the whole whatever thing that you're building for whatever thing that you're building that enables your thing to work. So we have a thing, control A, control E, okay, cool, V, and then what I want to go is in here. So here, suddenly we have a module here, and this module can access, it can reach into, we have a test module, we have an other test bench that can reach into other, okay? So now let's actually do some stuff. The first thing we're gonna do is wait some cycles here. I want to do something like #10, like wait some cycles just to see that wait some cycles so that things are set up, okay? And then the next thing I want to do is an initial begin, where I think there's somewhere where there's actually testing defined, Verilog testing. I did have a guide somewhere. Verilog. I want to use the one I have from before, so that we can actually go. I can make sure that I'm going properly. So we've done that. We've done the instantiation of the actual initial begin, and in here what we want to do, in here we want to do like an end, I think, an end. And in this end, what do we want to do in here? The first thing we want to do in this end is to do dump vars, and this is going to be 0, or rather, is it 0? Yeah, and this is going to be adder td. What does this do? This dumps all the way from dumps variables for the waveform for observation. Okay, so it basically makes a waveform for GTK wave to use. Okay, and then what do we want to do? I don't think we need to run clocks. What I want to do is I want to do if I want to set them to something, and then I want to pass in inputs and outputs. Verilog test benches. want to test them. Yeah, let's look at this. So that I want to, yeah, so there's this one and then there's that, but this one goes, this goes through a clock, and then I think the D large just changes with every clock. Okay, so let's do an initial begin, something like this. Somewhere before this, let's do another one, another initial begin, initial begin, and I don't know why that's not being highlighted, and there's something wrong here. I should have, oh yeah. I should just get the actual thing to tell me that this is me being lazy and not setting up my LSP for this. So what do we want in here? Let's set some actual sane variables. Let's set some defaults. Set some defaults. And I think I'm going to use the asynchronous assignment operator. Isn't that what I want to do? Don't I want to use the asynchronous assignment operator? Verilog test benches. I want to use that, yeah, so that's fine. I want num1. I would like num1, num_1. I want it to be 0. And then I'll do that. Num_2. I would want that to be 0 too. To be 0. And num_3. I want this to be 0 as well. Okay, cool. So now we've set like some defaults. Okay, so now and then we've made some sort of waveform. I don't know if this waveform is going to be very important, but let's actually keep going. Let's keep going. Let's keep going here. So we've done that, and what we want to do is want to randomly change the and enable. Yeah, so I want to write a for loop, some silly for loop that just runs through some numbers here. Let's do some for loop. I don't want to test and reset stuff. I want to just write some silly for loop that basically goes through 5 numbers and just ends. It just stops. Because I don't want it to be complicated, but I want it to work. I don't want it to be very robust. I just want it to work, okay? I just want it to work. So this and that, and then that in that, it does that. I don't want to use test vectors. Well, I might want to use test vectors. I just don't know what they are yet. Yeah, okay, cool. Let's look at this one. I want to start with a really simple one. That way, yeah, okay, cool. That has a... Ooh! We found it. So this is a port name. This is a signal name. This is a port name. This is a signal name. So this is the signal and the port. So and the instance name. So instance name, signal. We'll need to find out which one is which. Okay, cool. And then initial begin and and yeah. So this is that. So I don't want this. Yeah, we've made some inputs, we made some outputs. I just want some simple for loop that is going to actually go through some numbers. Like let's go like 255, 254. Let's add something like 260, 65, and sort of something like that. This one enables us shows us how to write individual test tasks. Maybe this is what we want. Okay. Reset release test 1. So I can write that, and I can go that. I can write another test I don't want to do a checker. Let's look at this one that I've written before. I want to do some sort of if dut1 r1 . display error count. Where's my assertions? These are not assertions, yeah? These are just displays. Where's my assertions? If that end error count plus 0, and then at the end error count equals 0, test pass, else begin test, display test failed, and then what? Display test completed with how many errors? Error count. So we can do the assertions and the tests in one. We can do the assertions and the tests in one by doing that and then setting them, and then what do we do? Doing that and the that, and then we add it. How do you get the module to? We set an input and a that and a that, and then we just check the output. And then we go next, and we set an input and we set an out, and we set two inputs and we check the output, because everything is parallelized and everything is happening all the time. We don't need to tell the thing to add it, because the thing knows to add. Everything is parallel and everything is happening all the time. Everything is happening all the time. So we never actually need to do anything here. We just need to pass in, we just need to set the this and the this, and then check what the output is. I don't know. I just don't know. So let's actually look at the test bench. Let's do something of the sort in the test bench and see what happens. So this is going to be a dump. I don't know if I even want a dump yet, because I don't know what that dump is going to do for us. Let's think about this. Simple Verilog test bench. Because if we know how to write modules and we know how to write modules and we know how to connect them, life gets so much easier, so much easier. Okay, but I don't see anything there. Yeah, this is fine. We don't need to invoke the module. We already have the module. So all we need to do is set something and then we just leave it. We set two things and then we just leave them and we see what happens. No. This has become something. Okay, so module multiplexer, input selector, input output that, assign that. That's fine. This is exactly the one we want to test. Okay, cool. So and then we want to go here and the clock is 0, set is 0, initial begin. We want to check all of those. That's fine. Complete test bench code. This is this. We want to do that. So what's happening here? Cell equals 1. What is happening here? Think about it. So we want to monitor, so because we want to look at it, and then what we want to do is we want to pass in some numbers, and then we want to do some equations. Cell equals 1, wait 1, wait one clock cycle and set it. What is happening here? This doesn't have assertions, but it will show everything that needs to be shown. So assign y is equal cell, select I or 0. If select is on, it's I1. If it's not, it's I0. So if select is equals to 0, 1, wait 1, select equals to 1. What are you showing me here? What are you showing me here? What are you showing me here? You're setting I know what you're doing. What is the end thing? What is the result from here? What is the result? Y. So you're checking the value of y based on what you're setting in select. I is equals to 0, I1 is equals to 1. So that's the thing. This is exactly the thing I was saying. We don't need to invoke the module. We just need to set things. We just need to set the inputs and check the outputs. I see. So check all the outputs. So check values of inputs and outputs. Everything is happening all the time. Everything is happening all the time. So you don't need to call a function. This is the difference between like the software part and this part. You don't need to call a function for it to be invoked. It's already invoked. And this is where like software is let's go backwards. Okay, let us do dump them, and then we'll see what happens. And then I want to do print values, and then I want to do a monitor, and then in here I want to do a simple print statement, and in this statement I want to say num sum is equals let's do a d, and then it doesn't know, does it? Okay, cool. It doesn't care that num1 is equals d, and then why is that like that? So weird. Okay, cool. It's fine. And then num2 is equals d, isn't it? And then I don't need anything. I don't need anything else. So and then in here I want to pass in the actual variables that I want, which is num1, sum num1, and num2, and then that actually gives us our test bench. Okay, and then in here, let's go. We've already set them up there. We've already set some defaults up here. So we can just, what we want to do is we want to do this. Because we have a monitor, every time they change, every time these values change, they will be shown on the screen. And then we can do a few of them. So what I want to do, I wouldn't set them now, and I would just go num1 is equals 60, 50, and then I will do another num2 is equals 70. Let's see what happens there. And then we are gonna do hash3, just wait a bit. Num1, actually let's do something like 100 so that we actually get to see stuff changing. Num1, well, they'll just print really fast, equals 120, and then num2 is equals 0, and then let's do hash 100, and then equals something like num1 is equals num1 is equals 250, and num2 is equals 251, something like that. Yeah, and then we can do we can leave it at that. So it's just 3 of them, and then this needs actually to be terminated, and then that is it. This is our test bench. Monitor, what monitor does is every time a value changes, that thing is run. Okay, so anytime a value in this list changes, that line will be run, and if that line is run for every time this value changes, we can see the sum. We can actually come here, see sum of. Can I do that? And then come back here and do something like that. Actually, let's just do that, and then okay, let's do that. Let's go into here, and then we're gonna go like sim. What happens? Invalid module item. Syntax test. Appear TB number 15. Other number 15. Okay, so this is the issue. I've used this delay before, so let's go and see how we can set that delay. There's this delay over here. So are you telling me I just don't need this delay? Just let it happen by itself? Syntax error 27. Syntax error number 27. 26J. So there is some sort of syntax error in here. Should be a monitor I can use. Monitor. Do I need to go dut dot sum dut dot num and dut device under test dot? Is that what I need to do? Malformed statement. What do I want to do? I could also just use hexes, but I don't know. Let me look at that. Pretty good. There's only displays. I can see that. Perhaps I can use displays instead of monitors. Let's actually see. display. Maybe that's the issue. Up your sim. Malformed statement. Okay, cool. That's human. Where is the problem? Maybe these are not allowed. Maybe these are not allowed. Maybe I just need to do let's see. I didn't want to use hexadecimals because I didn't want to convert them, but it's fine. We're just doing 3 sums. We can actually just do conversions. Okay, cool. So I'm missing something less than that. Equals that, equals that, equals that. X1, x2, x3. Yeah, here's the decimal that I was thinking about. 0 decimal, 0 decimal. Zero D. Is that how I'm messing up? 0D and then 0D. First of all, let's look at it. Slow cycle number something, PC is equal to something, IR is equal to something, RGB is equal to something, it's binary, bit. Okay, cool. That should be good. Is that what I'm missing? No. Something's up. Do I need the equal signs? Yeah, the equal signs don't matter at all. So there's something I'm missing. Duty dot. Lead. Let's see how we're using lead red. Okay, cool. So those I'm not missing those. So it's not here because this can be accessed completely by themselves. They can be seen. Can anyone see what I'm doing wrong? Can anyone see what I'm doing wrong? 1 decimal, 2 decimal, 3 decimals. There's a space and then there's that. Where am I going wrong? Monitor, and there's a thing at the end, and this is 1, 2, 3, 4. Wait, 1, 2, 3, 4. Not a problem. So let's look at the complete one. Reg that, wire. Wire Y is a hexadecimal. That's why. Yeah, I can't do that. So that's not the actual issue. Something else is the issue. Somehow. There's that one and then there's this. So where's the issue? Does anyone see what I'm doing wrong? Please, if you do see what I'm doing wrong, please let me know. Now 27. If we do that and just see, can we do that? Does the rest of the thing actually work? 29. Can anyone see what I'm doing wrong? They're declared as input and output, so I can just say let green, let blue, red out. So that's not the actual issue. You see what here? There's an issue here. It's going to be something so small. It's going to be something super tiny. I can't believe this. This is going to take the second hour of my stream to do this. What is it? What am I missing? I hate to disappoint you guys. I hate to disappoint you. I hate to disappoint you. I found out what I'm doing wrong. So num1 is declared as a wire. We do have a wire led red in there. So what do we? Okay, it is working. Num1 is not a valid L value for procedural assignments, so that's fine. Do you want me to do some sort of assign like that? Is that what you want me to do? Okay, can I do assigns then? What did I do wrong now? So it's something about the way I'm setting num1. Wait, so this the thing before is going okay. So this is working okay. So if I go like that, if I go like that and I do that and I do if I do that, what happens? Did I save? Written, yeah. This is number 29 and number 30. 18, 18, 19, 20, 29, 30. Oh, okay, cool. So that's okay. That's fine. It's failing from all the way from the beginning. All the way from the beginning. So let's actually look at another test bench that I have that existed before. And I don't know. What would we like to do here? It doesn't like this here. This is 18. This is 18. So what if I do here? What if I do here? What if I do here? So let's first of all, so from eating num1 is not a value. It's not valid for procedural. Do I need to just do away with my initial begin? Is it because reg can hold stuff? So reg can hold stuff, y cannot hold anything. So is that why? Is this why? So cannot perform procedural assignment to sum because it's always this. Is that? Okay, cool. I don't care about this. I really don't want to set you. What I want to do is to be able to simulate. Anyways, 50 plus 70, 120. 120 plus 0, 120. 501. 250 plus 251, 501. Here we go. Our test ring. We have successfully walked our way precariously into writing a test bench that works all the way from scratch. We wrote the module from scratch. We wrote the test bench from scratch. We walked through all the errors that we found, and we finally have a module that works and a test bench that works. And we know how these things are connected and where they're connected to and from. I'd like to look at this and see if can we do that? Can we do that? Can we do that? And then what happens here? What if I rerun them? So these are actually, I think they're shown in so you can move through time, and by virtue of being able to move through time, I think they will change. So yeah, we did it. So we basically managed to write a test bench for a module that we wrote, and we managed to, along with it, we wrote, what did we do? Okay, so let's be clear. What did we do? We wrote a module. Let's actually commit this code so that it's, we wrote a module. So we wrote an adder module. Here it is. And what this adder module does is has two inputs, which are 8-bit numbers, and then it has an output, which is a 9-bit number. And what it does an assign. It assigns a sum to an expression that is the sum of num1 and num2. And then after we wrote this module, we discovered that if something is a top level module in Verilog, and it has an input and an output, the top level module input and outputs need to be defined in the PCF file. However, this module that we are working with right now is not a top level module. Okay, so what we did is we changed our initializer to say that our top level module is a main, and we made a main empty module that has some register that we don't use right now, and then we also have an empty pin constraints file. Okay, cool. So And then we went further, and after going further, what we did is we declared a test module, a test bench for our module. We made a device under test for the actual other module that we are testing, and then we set our defaults of num to num1 and num2 to 0, and then after that we did a dump vars which dumps variables into a waveform so that we can actually test this. And then we wrote a monitor statement, and the monitor statement looks at the variables that are set within that statement, and what it does is what it does is every time those variables in those statement changes, it prints out something. So as you can see here, every time the variables change, so the sum is 120, then num1 is 50 and 70. The sum is 120, num1 is 120, num2 is 0. The sum is 501 of num1 and 250 and 251. So what did we do? If you look at this thing that we have here, what we did here is we made a system verilog design. It has 2 inputs and 1 output, and we made a test bench to exercise the block and print out the input to a console. Bit width analysis. What is the range of unsigned numbers that can be represented by 2 bits? 2 bits is 2 power 2 minus 1, so it's going to be 2 power 2 minus 1 is 4, which is 0 to 4. 3 is 2 power 3, something like 8, and then to 7. 8 is 2 power 8, which is something like, what is 2 power 8? 2 power 8 minus 1, and 16 bits is 2 power 16 minus 1. Anyways, whatever. And the pattern you're meant to see here, if you actually see 2 power 2, the pattern we're meant to see here is 4. Okay, so let's look at that. And then what is 2 power 2 is 4, and then is there a power here that I can use? So what about a 2 power 3? This is going to be double. 2 power 3 is 8. Okay, 2 power 4 is going to be 16. See, so when you go up 1 bit, you double the amount of stuff that you can you double the amount of stuff that you can save in that thing. So that's the observation there. And then what is the minimum number of bits it takes to represent the sum of 2 numbers? The sum of 2 numbers, e.g. if 2 numbers are represented by 2 bits each, the minimum number of bits is 2 there. How many bits does it take to represent their sum? 2. The minimum. The maximum could be more. Because if you went to both the edges, if you added 255 and 255, you would make a number that overflows the edges of the bits, and then you would need the next one basically. So the minimum. What if the inputs are 3 bits instead of 2 bits? So the minimum is 3 bits there. What if one of the numbers is represented by 2 bits and the other one by 3 bits? I would say the minimum is 3 bits as well. What if the operation or the difference of the 2 numbers? I would say same, 2 bits. I would keep it at that. I might be wrong. What if the operation were a multiplication of the 2 numbers? So that now becomes a problem. If the operation, so let's go 2 times 2. This is 4. So this is a weird one. So 2 plus 4, 10 is equals to 12. Yeah, 12 is within 2 power 4. Yeah, okay, but 2 times 100 is 200, and 200 is within 2 power 8 or something. No, 2 power 8, 2 power 8. 2 power 8, yeah, 256. So I still don't know what to conclude from there. What is the least number of bits? that would be used to represent 100 is something that is 128, so that's 2 power 7, and 2 is a 2 power 1. So I think so if you multiply them, it's 200, and 2 power 7 is the less. So I would say you add the both of them. So it would be like, if it's 2 bits and 2 bits, then it's 4 bits. Okay, so let's say 2 bits is 4. Okay, 2 power 2. 2 power 2 is 4. What's the maximum? 16. 2 power 2. 2 power 2. What is the maximum here? 4. Well, 4, yeah, okay, cool. And then let's say 2. So 4 times 4. 4 times 4. 4 times 4. 60. And in order for this, you need 2 power 4. 2 power 4. 16. So I would say the bits, the thing is, for us to say the maximum number that can the multiplication is going to be 2 plus 2. So you add the bit number. So if it's a 3-bit number plus a 2 times a 2-bit number, you add the bit number and you go like you would need a 5-bit number to represent them. That's what I would say. And then what else? Advanced challenges. What if there are too few bits to represent the result of an operation? Let's actually put that in and see how that works. So let's do that here. Let's do that here. And I'll remove the simulator here. I'll remove this. I will remove that so that in here, and I would say wait 100. Wait 100. Oh, actually, can I just do that? Can I just go boom and just leave it? No, I should. This should be syntax errors, but it somehow works. Okay, cool. So there's that, and then let's set num1 is equals 255, and then num2 is equals to 255. So 255 plus 255, 255 plus 255, because 2 power 8 is 256, no? 255. Yeah, minus 1. So 2 power 9 is what? 2 power 9 is 512, is 510. 511. 511. And 255 plus 255, 510. I would like a way to make it go past that. Yeah. But because I've already said this is an 8-bit number, if I've already said this is an 8-bit number, it's, I don't know. I think it would just truncate. That's what I think it would. I think it would just truncate. I really think it would just truncate because I can't do that. I already have a rule that says it won't go past that. So I can't really go like 257 here. I mean, can we? Can we? 27. see, so it just. Oh, I know what happened. It rolled over. It rolled over. It rolled over. So if we go 255, which is the maximum, and 255, which is the maximum, yeah, it will roll over. It's gonna be 0. So it rolls over. That's what happens. So 256, let's say. These are two maximums. So 256. Let's go 511. It rolls over. When it rolls over and it just uses whatever it's carrying forward. It uses whatever it's carrying forward. Okay, cool. And what if I do rm-rf underscore build? And I sim it. Yeah, it doesn't care about the VCD. It wants to see. So it rolls over. Basically, that's what happens. It rolls over. How to represent signed numbers in Verilog. Tools complement. Change your order to use signed arithmetic, and what is the minimum bits needed for the operations of the numbers that are signed instead of unsigned. I think they take double. I'm not so sure. How to implement more complex arithmetic like divide, square root, cosine, sine, and cosine. First of all, do we have the Verilog quick reference? So Control F, cos, sine, sin. No. So divide. Yeah, there's a division and there's a multiplication. So I think those ones we're going to discover as we go along. So let's actually just make this into some module somewhere, and we can leave this Gaiocho's, GitHub Gaiocho, and we go in here and we go new repository, and we can say RTL ada plus T. Okay, and ada module plus an associated test bench for the module. Create repository. It's private. It shouldn't be private. So I don't think this affects anything. You can't see anything here, so change visibility, may change the public. Yeah, sure. Make this repository path. I can't do this. This is going to be risky because then if you guys can see this, okay, I don't know, I'm just gonna do it on off screen. Just be safe, because if you guys can see this, one of you guys knows how to make it so that, because you know the time I'm doing it, you know why I'm doing it, so someone knows how to make it so that I can lose something. Yeah, okay, cool. So that's set up. Okay, that's set up there, and what we want to do is we actually want to just connect this into let's see, git status, git init, git branch -m main, and then in here what I want to do in here is I want to make git ignore, and then what I want to do here is ignore underscore build directory, and then I'll do that, and then let's here, git status, git add, git commit -m initial working other module with the associated test bench. Okay, cool. Git I wanna do that, and then git git push -u origin main. And then the other thing I want to do is add this to the repository, so to the videos, so that a code we will be working on. Yeah, Control V, and there's a code that we're working on. As always, as always, thank you so much if you watched this far. If you want to support the work I do, if you want to help me get this done, I do have github.com, github.com. I do have a sponsor page, and you can actually sponsor me if you want, buy me a coffee and things of the sort, and yeah, you can do that. You can do that support if you want. Cool. Thank you so much. It's been amazing. That was today. I'll see you tomorrow, and I think that's the nice thing about working on these things every day. So tomorrow we're going to move on with week 3, and we're going to do the material and see what's up, and think about stuff of the sort that we want to do. But yeah, thank you so much for showing up. What we worked on today was an other module, and the more interesting part was actually writing a test bench for it and getting that going, and getting very intuitively familiar with writing very low test benches. So thank you so much. I shall bid you adieu, and I will say, remember to be daring as far as you can, as best as you can. Thank you, and see you next time.